I'm so glad you found your way here tonight. Maybe you've been scrolling endlessly. Maybe your mind won't settle. Or maybe you're just the kind of person who finds peace in the vast, strange truths of the cosmos. Either way, you're exactly where you need to be. Tonight, we're not just learning about space. We're drifting through the most extreme, bizarre, and mind-bending objects the universe has ever created. Things so strange they barely seem real. Neutron stars that could erase every piece of technology on Earth from thousands of miles away. Black holes wandering through the darkness between galaxies like cosmic predators. Stars made of diamond. Explosions that outshine 100 billion suns. These aren't science fiction. They're out there right now, spinning, burning, colliding in the endless dark. And as you listen, you can let go. Let your breathing slow. Let your thoughts drift like dust through a nebula. Because tonight, you've got nothing to do but rest and wonder. And just before we begin, if these cosmic journeys help you unwind, if they give you a gentle way to end your day, consider liking and subscribing. It helps other curious minds find their way here, one sleepy soul at a time. Now, let's begin with something truly extraordinary. Magnetars are the universe's most magnetic objects, and they are terrifying in the most beautiful way. Imagine a neutron star, already one of the densest objects in existence, a ball of nuclear matter only 20 kilometers across but containing more mass than our entire sun. Now, imagine that this star has a magnetic field a quadrillion times stronger than Earth's. That's a magnetar. These objects are so magnetically powerful that they warp the very atoms around them. If a magnetar existed just halfway between Earth and the Moon, about 200,000 kilometers away, it would erase every piece of magnetic data on the planet. Credit cards, hard drives, magnetic strips, all gone in an instant. But you wouldn't be around to notice because the magnetic field would also be pulling the iron from your blood. At closer distances, the tidal forces and radiation would disintegrate matter itself. The magnetic field is so intense that it creates an effect called vacuum birefringence, where empty space itself becomes polarized and begins to behave differently in different directions. Light passing near a magnetar gets twisted and split. The surface of a magnetar is a nightmare realm of crustal mountains, nuclear matter frozen into crystalline structures, and magnetic field lines twisted into impossible knots. Occasionally, these field lines snap and reconnect in what's called a starquake. When this happens, the magnetar releases more energy in 1/10 of a second than our sun releases in 100,000 years. This energy bursts out as gamma rays and X-rays, creating what astronomers call a soft gamma repeater. These flares have been detected from magnetars thousands of light years away, and they're bright enough to affect our own atmosphere. In December 2004, a magnetar called SGR 1806-20 erupted with the brightest blast of energy ever recorded from beyond our solar system. For 1/10 of a second, it was brighter than anything in the night sky except the moon. The radiation hit Earth's upper atmosphere and ionized it, disrupting radio communications. This happened from an object 30,000 light-years away. Magnetars are born from the collapse of massive stars, but only under specific conditions. The star must be rotating rapidly as it dies, and it must have an incredibly strong magnetic field to begin with. As the core collapses down to a sphere just 20 kilometers wide, conservation of angular momentum spins it faster and faster, and the magnetic field gets compressed and amplified. The result is an object spinning perhaps 600 times per second, with a magnetic field that defies comprehension. These objects don't last forever. Magnetars are young, usually only a few thousand to a few tens of thousands of years old. Their magnetic fields are so powerful that they actually drain the star's rotational energy. Over time, the magnetar slows down, the field weakens, and it fades into a more ordinary neutron star. But during their brief, violent youth, magnetars are among the most extreme objects the universe can create. There are only about 30 confirmed magnetars known in our galaxy, but there may be tens of millions of dead ones, now silent and cooling, scattered through the Milky Way's history. Rogue black holes wander through space like cosmic ghosts, and they are perhaps even more unsettling than magnetars because they are invisible and nearly impossible to find. When galaxies collide and their central supermassive black holes eventually merge, the merger doesn't always happen symmetrically. If the two black holes have different masses or spins, the gravitational waves they emit during the merger can be stronger in one direction than another. This creates a recoil effect, a gravitational rocket that can kick the merged black hole out of the galaxy entirely. These rogue, supermassive black holes, each containing millions or even billions of times the mass of the Sun, are flung into intergalactic space at speeds that can exceed several thousand kilometers per second. They travel alone through the dark, no longer anchored to a galaxy, no longer feeding on surrounding gas and stars. Without material to consume, they produce no light, no X-rays, no radiation of any kind. They become invisible wanderers, detectable only if they happen to pass in front of a distant star and cause gravitational lensing, briefly magnifying and distorting the starlight. Astronomers estimate that there could be hundreds or even thousands of these rogue, supermassive black holes drifting through the universe, ejected from their home galaxies during ancient collisions. Some may eventually be captured by another galaxy, settling into a new core. Others will drift forever, moving through the cosmic web with nothing but dark matter and stray hydrogen atoms for company. The idea of invisible, galaxy mass singularities roaming the universe is deeply strange. They're out there, right now, traveling through the space between galaxy clusters, carrying with them the warped space-time of their event horizons. If one were to pass near our solar system, we would only know about it from the gravitational disturbances it caused, the subtle tugging on orbits, the bending of light from distant stars. But space is vast, and the likelihood of such an encounter is vanishingly small. Still, it's a reminder that the universe contains dangers we cannot see, wandering silently through the dark. Quasars are the brightest objects in the universe, and their existence reveals something profound about the cosmos. A quasar is what happens when a supermassive black hole feeds voraciously. At the center of most large galaxies lies a black hole containing millions or billions of solar masses. Usually, these black holes are relatively quiet, consuming gas and dust at a slow, steady rate. But in the early universe, and occasionally even today, conditions allow vast amounts of material to fall toward the black hole at once. As this matter spirals inward, it forms an accretion disk, a swirling maelstrom of gas heated to millions of degrees by friction and compression. The disk doesn't fall directly into the black hole. Instead, it orbits faster and faster as it gets closer, and the inner regions become so hot that they radiate enormous amounts of light across the entire electromagnetic spectrum. Jets of particles and radiation, accelerated to nearly the speed of light by the black hole's magnetic fields, shoot outward from the poles. The result is a quasar, an active galactic nucleus so luminous that it can outshine every single star in its host galaxy combined. Some quasars emit more light than 1,000,000,000,000 suns. They can be seen from across the universe, billions of light years away. When we observe distant quasars, we're looking back in time to the universe's adolescence, to an era when galaxies were smaller, closer together, and collisions were more frequent. These collisions funneled gas toward the central black holes, igniting them into brilliant beacons. A supermassive black hole powering a quasar can consume at mass equivalent to 1,000 suns every single year. This creates so much energy that the radiation pressure can blow gas out of the galaxy entirely, in powerful winds that travel at thousands of kilometers per second. These winds shape the evolution of galaxies, regulating star formation and redistributing elements across intergalactic space. Quasars were far more common billions of years ago. As the universe aged, galaxy collisions became less frequent, and the supermassive black holes at galactic centers exhausted the nearby gas supply. Today, most supermassive black holes are dormant or only faintly active. The Milky Way's own black hole, Sagittarius A star, is nearly silent. But in the distant universe, we can still see the light from ancient quasars, radiation that has been traveling toward us for most of cosmic history. Looking at a quasar is like looking at a cosmic lighthouse from the universe's youth, still shining across the void. Neutron stars are objects so dense that they break the rules of ordinary matter. When a massive star exhausts its nuclear fuel, its core collapses catastrophically. Electrons are crushed into protons, forming neutrons, and the core becomes a sphere of neutron-degenerate matter, held up only by the pressure that arises from the quantum mechanical principle that neutrons cannot occupy the same state. The result is a star made entirely of nuclear matter, packed so tightly that a sugar cube-sized piece would weigh about 1,000,000,000 tons on Earth. The entire mass of our Sun compressed into a sphere just 20 kilometers across. If you could somehow stand on the surface of a neutron star, you would be flattened instantly. The gravity is so intense that it warps space-time severely. Light emitted from the surface is red-shifted by the gravitational field. The escape velocity is about half the speed of light. Mountains on neutron stars, irregularities in the crust caused by magnetic stresses, are only a few centimeters tall because gravity pulls everything down with such overwhelming force. Neutron stars spin. Most rotate many times per second, and some, called millisecond pulsars, spin hundreds of times per second. The fastest known pulsar rotates 716 times every second. At that rotation rate, a point on the star's equator is moving at about 20% of the speed of light. If the neutron star were spinning any faster, centrifugal force would tear it apart. These objects emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like a lighthouse. If the beam points toward Earth during its rotation, we detect regular pulses of radio waves, X-rays, or gamma rays. This is why they're called pulsars. The regularity of these pulses is extraordinary. Some pulsars keep time more accurately than atomic clocks on Earth. Neutron stars cool over time, radiating away their internal heat into space. Young neutron stars can have surface temperatures of 1,000,000 degrees, but older ones cool to a few 100,000 degrees. Eventually, over trillions of years, they will cool completely and become black dwarfs, cold spheres of degenerate matter drifting through the galaxy. But we're nowhere near that timescale yet. the universe is only about 14 billion years old, so even the oldest neutron stars are still relatively warm. Inside a neutron star, the conditions are even more extreme. The outer crust is a lattice of neutron-rich nuclei, but deeper down, matter exists in forms we can barely understand. There may be layers of superfluid, neutrons, regions where protons form a superconducting fluid, and perhaps even a core of quark matter, where the neutrons themselves break down into their constituent quarks. We don't know for certain because we can't replicate these conditions in a laboratory. Neutron stars are natural experiments in extreme physics, teaching us about matter at densities that will never exist anywhere else in the universe, except perhaps during the first moments after the Big Bang. Fast radio bursts are one of the universe's newest mysteries, and they are deeply strange. These are incredibly brief flashes of radio waves, lasting only a few milliseconds, that come from distant galaxies billions of light-years away. Despite their short duration, each burst releases as much energy as the Sun emits over several days. They were first discovered in 2007, when astronomers noticed an unusual signal in archived data from the Parkes radio telescope in Australia. At first, it was unclear whether the signal was even real or just interference. But more bursts were found, each one unique, each one powerful, and each one coming from far outside our galaxy. For years, astronomers couldn't figure out what was causing them. The bursts seemed to come from random directions in the sky, and they didn't repeat, so there was no way to study a single source in detail. Then, in 2016, one fast radio burst repeated. This allowed astronomers to pinpoint its location to a dwarf galaxy about 3 billion light-years away. Since then, a handful of repeating sources have been found, and the mystery has only deepened. What could produce such an intense, brief flash of radio energy? The leading candidates are magnetars, those ultramagnetic neutron stars. The idea is that starquakes or flares on a magnetar's surface could accelerate particles to high speeds, generating a brief but intense burst of radio waves. Some observations support this. In 2020, a magnetar in our own galaxy produced a burst of radio waves that resembled a fast radio burst, the first time such an event had been seen from a known source. But not all fast radio bursts fit this model. Some seem to come from environments without obvious magnetar activity. Others show strange, repeating patterns or polarization that's hard to explain. A few bursts have been detected at multiple wavelengths simultaneously, not just radio, which suggests a more complex emission mechanism. The rate at which fast radio bursts occur is staggering. Estimates suggest that thousands happen every day across the entire sky, though we only detect a small fraction of them. Each one represents a cosmic event of tremendous energy, and yet we still don't fully understand what causes them. They are a reminder that the universe is full of phenomena we've only just begun to discover. Signals reaching us from the deep cosmos that we're still learning to interpret. Hypervelocity stars are stars that move so fast they can escape the Milky Way entirely, and their existence tells us something dramatic about the violence at the galaxy's core. Most stars orbit the galactic center at a few hundred kilometers per second, held in place by gravity. But hypervelocity stars travel at speeds exceeding 1,000 kilometers per second, and some move even faster, up to 3,000 kilometers per second. At these speeds, they are no longer bound to the galaxy. They will travel outward forever, into the space between galaxies. The mechanism that creates hypervelocity stars is extreme. The leading explanation involves the supermassive black hole at the Milky Way's center, Sagittarius A star. If a binary star system wanders too close to the black hole, the intense gravity can rip the pair apart. One star is captured by the black hole and spirals inward, while the other is flung outward like a stone from a slingshot. The energy comes from the orbital motion of the binary and the gravitational potential of the black hole. The ejected star carries away enough momentum to reach escape velocity. Astronomers have identified dozens of hypervelocity star candidates, most of them located in the outer halo of the Milky Way, moving at incredible speeds and heading outward. By tracing their trajectories backward, many appear to originate from the galactic center. These stars are effectively exiles, cast out by one of the most violent gravitational interactions possible. Another possible mechanism involves supernova explosions in binary systems. If one star explodes and the explosion is asymmetric, it can give the companion star a gravitational kick, accelerating it to high speed. This might explain some hypervelocity stars that don't appear to come from the galactic center. Hypervelocity stars are fascinating because they will spend the rest of their lives traveling through intergalactic space, far from any galaxy. They will age, burn through their fuel, and eventually die alone in the void. If any planets orbit these stars, those worlds will drift through a sky nearly devoid of stars, with only the faint smudges of distant galaxies visible. It's a lonely fate, but also a remarkable one. These stars are travelers, wanderers carrying a piece of the Milky Way into the greater universe. Zombie stars are white dwarfs that somehow survive their own supernova explosions, and they are among the strangest stellar remnants known. A white dwarf is the cooling core of a sun-like star, about the size of Earth but with roughly the mass of the Sun. If a white dwarf is part of a binary system and it siphons matter from its companion, it can gain mass. There's a limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun, beyond which the white dwarf cannot support itself. When a white dwarf exceeds this mass, it explodes in a Type Ia supernova, one of the brightest and most consistent types of supernova in the universe. The entire star is destroyed, blown apart in a thermonuclear detonation that releases as much energy as the Sun will emit over its entire lifetime. Or so we thought. In recent years, astronomers have found evidence of white dwarfs that appear to have survived their own supernova explosions. These are called zombie stars or runaway survivors. The leading explanation is that these stars underwent a partial supernova. Instead of completely detonating, only the outer layers exploded, blasting away a significant portion of the star's mass. The explosion was powerful enough to classify as a supernova, but not powerful enough to destroy the core. What remains is a white dwarf moving at extremely high speed, propelled by the force of the explosion. Some of these stars are traveling at thousands of kilometers per second, fast enough to escape their host galaxies. They are faint and difficult to detect because white dwarfs emit very little light, but their high velocities and unusual chemical compositions give them away. The surfaces of these zombie stars are enriched with elements produced during the partial explosion, elements like calcium, iron, and other metals that wouldn't normally be present in a white dwarf's atmosphere. This suggests that the star experienced a violent event, but didn't fully disintegrate. The existence of zombie stars has implications for our understanding of supernova and cosmology. Type Ia supernova are used as standard candles to measure cosmic distances because they're thought to have consistent peak brightness. But If some type Ia events don't fully destroy the star, that introduces variability. It means we need to refine our models and be more careful when using these explosions to map the universe. These stars are survivors in the most extreme sense, remnants of an event that should have annihilated them entirely, now traveling alone through the galaxy at breakneck speed. The Great Attractor is a gravitational anomaly that pulls our galaxy and thousands of others toward it at incredible speed, and we still don't fully understand what it is. The Milky Way is moving through space at about 600 kilometers per second, not just because of the universe's expansion, but because it's being pulled by a concentration of mass in a specific direction. This region lies roughly in the direction of the constellations Hydra and Centaurus, about 200 million light-years away. The problem is that the Great Attractor is located behind the zone of avoidance, a region of the sky obscured by the dense gas and dust of the Milky Way's disk. In visible light, we can't see what's there. Radio and infrared observations have revealed that the region contains several massive galaxy clusters, including the Norma cluster and parts of the Shapley supercluster. The combined mass of these structures creates a gravitational pull strong enough to influence the motion of our local group of galaxies and everything around it. But the Great Attractor is not the end of the story. Beyond it lies an even larger structure, the Shapley supercluster, which contains tens of thousands of galaxies and exerts an even stronger pull. Our motion through space is the result of a complex interplay of gravitational influences, a cosmic tug-of-war between different mass concentrations spread across hundreds of millions of light-years. What's fascinating is that this motion reveals the universe's large-scale structure. Galaxies are not spread evenly through space. They cluster together along filaments and sheets, separated by enormous voids. The Great Attractor is part of this structure, a dense node in the cosmic web where matter has accumulated over billions of years. Studying the Great Attractor and the motion it induces helps astronomers map the distribution of both visible and dark matter on cosmic scales. It reminds us that even though we think of the Milky Way as our home, we are not stationary. We are part of a larger flow, drifting through space along invisible currents shaped by gravity and the distribution of mass left over from the Big Bang. And now, let the stars begin to blur behind your thoughts. We've drifted through magnetars and rogue black holes, through quasars blazing with the light of 1 trillion suns, through neutron stars and hypervelocity exiles. You've learned of fast radio bursts and zombie stars, and the Great Attractor pulling us silently through the dark. These are not just facts. They are windows into a universe stranger and more wondrous than we ever imagined. And you are part of it. Your atoms were forged in stars. The iron in your blood came from a supernova. The calcium in your bones was created in stellar fusion. You are made of the cosmos, resting now, drifting gently toward sleep. We're venturing into the nature of time, distance, and scale. The universe is not just vast. It is so incomprehensibly large that our minds struggle to grasp it. Light itself, the fastest thing that exists, takes billions of years to cross it. Time bends and stretches near massive objects. The universe expands faster than anything within it can travel. And somewhere out there, beyond what we can ever see, the cosmos continues forever, or folds back on itself, or ends in ways we cannot yet imagine. So, settle in. Let your breathing slow. Let your thoughts drift like photons through the void. Because tonight, we're traveling through time itself. measured in the patient crossing of light through an ever-expanding universe. And before we begin, if these journeys through space help you find peace at the end of your day, consider subscribing. It helps others discover this quiet corner of the universe, one restful mind at a time. Now, let's begin. Light from the most distant galaxies has been traveling toward us for over 13 billion years. And when we look at these galaxies through our most powerful telescopes, we are not seeing them as they are now. We are seeing them as they were in the universe's childhood, when the cosmos was less than a billion years old. This is one of the most profound aspects of astronomy. Looking out into space is the same as looking back in time. Light travels at exactly 299,792,458 meters per second in a vacuum. This speed is absolute, the same for all observers regardless of their motion. Nothing can travel faster. When light leaves a distant galaxy and travels across the universe toward Earth, it carries information about what that galaxy looked like at the moment the light departed. If a galaxy is 10 billion light-years away, the light we see tonight left that galaxy 10 billion years ago, when the universe was only about a quarter of its current age. At that time, galaxies were smaller, more irregular, and filled with vigorous star formation. The universe was denser, hotter, and more chaotic. By observing distant galaxies, astronomers can watch cosmic history unfold. They can see how galaxies evolved over time, how they merged and grew, how star formation rates changed, and how the large-scale structure of the universe developed. The most distant galaxies we've detected formed when the universe was only a few 100 million years old, shortly after the first stars ignited. These galaxies are faint and red-shifted, their light stretched by the expansion of space itself. They appear to us not as bright spirals, but as small, irregular clumps of stars, the building blocks that would later merge to form the grand galaxies we see closer to home. Some of the light reaching us tonight began its journey before Earth even existed. Our planet formed about 4.5 billion years ago, but light from galaxies 9 or 10 billion light-years away started traveling toward us long before our sun ignited, before our solar system's dust disk had coalesced into planets. This light passed through intergalactic space for billions of years, through regions filled only with thin hydrogen gas and dark matter, across voids hundreds of millions of light-years wide, until finally it reached our telescopes. When you look at an image of a distant galaxy, you are seeing an object that may no longer exist in that form. It may have collided with another galaxy, or exhausted its gas supply and ceased forming stars, or evolved into something completely different. We will never know what it looks like now, in our present moment, because the light showing us its current state will not arrive for billions of years. This is the strange, beautiful nature of cosmic observation. We are archaeologists of light, studying the preserved images of a universe long past. The edge of the observable universe is about 46 billion light-years away, and this number surprises many people because the universe is only 13.8 billion years old. If light has only had 13.8 billion years to travel, shouldn't the most distant object be 13.8 billion light-years away? The answer lies in the expansion of space itself. The universe is not static. It has been expanding since the Big Bang, and this expansion stretches the space between galaxies. When light left the most distant galaxies we can see, those galaxies were much closer to us, perhaps only a few billion light-years away. But as the light traveled through space, space itself expanded. carrying those galaxies farther and farther from us. By the time the light reaches us today, those galaxies are now about 46 billion light-years away. This expansion is not galaxies moving through space. It is space itself growing, like dots on the surface of an inflating balloon. The dots don't move across the balloon's surface, but they get farther apart as the balloon expands. In the same way, galaxies are not flying away from us through space. Space is expanding between us and them. The observable universe is defined by the cosmic light horizon, the boundary beyond which light has not had enough time to reach us since the Big Bang. Anything beyond this boundary is outside our observable universe, not because it doesn't exist, but because its light hasn't reached us yet. And because the universe is expanding at an accelerating rate, some regions that are currently beyond our light horizon will never become visible. Their light will never catch up to us because the space between us and them is expanding faster than light can cross it. This means there are galaxies, potentially infinite numbers of them, that we will never see, no matter how long we wait or how powerful our telescopes become. They exist in a part of the universe forever separated from us by the expansion of space itself. Time dilation near black holes becomes extreme, and this effect has profound implications for anyone or anything that ventures close to an event horizon. According to Einstein's theory of general relativity, gravity warps space-time. The stronger the gravitational field, the more space-time curves, and one consequence of this curvature is that time passes at different rates depending on how deep you are in a gravitational well. Near a black hole, this effect becomes dramatic. Imagine you have a friend who descends toward a black hole while you watch from a safe distance. As your friend approaches the event horizon, time for them, as measured by you, appears to slow down. Their movements become sluggish. Their clock ticks slower and slower. If they were to hover just above the event horizon and then return to you, they would have aged only a short time, but you might have aged decades or even centuries, depending on how close they got and how long they stayed. This is not an illusion. It is a real, physical consequence of space-time curvature. Time genuinely passes at different rates in different gravitational fields. For the person near the black hole, everything feels normal. Their heartbeat, their thoughts, their watch, all tick along at the usual rate. But relative to someone far from the black hole, they are experiencing time in slow motion. This effect has been measured in much weaker gravitational fields. Atomic clocks flown on airplanes run slightly faster than identical clocks left on the ground because they are farther from Earth's center and experience slightly weaker gravity. GPS satellites must account for this effect. Their clocks run faster than clocks on Earth's surface by about 38 microseconds per day. If this correction were not applied, GPS coordinates would drift by kilometers within days. Near a black hole, the effect is far more extreme. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer. If you watched someone fall into a black hole, you would never actually see them cross the horizon. They would appear to slow down, freeze, and gradually fade from view as the light from them becomes more and more red-shifted. But from their perspective, they would cross the horizon in a finite amount of their own time, and once across, they would be pulled inexorably toward the singularity at the center. This strange asymmetry between perspectives is one of the most unsettling features of black holes. The event horizon is a one-way boundary in space-time. Cross it, and you are severed from the rest of the universe. The cosmic microwave background is the oldest light in the universe, and it fills every cubic centimeter of space with a faint glow left over from the Big Bang. About 380,000 years after the universe began, it had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, a hot plasma where photons constantly scattered off free electrons. But once atoms formed, photons could travel freely. This is called recombination, and the light released at that moment has been traveling through space ever since. Today, that light reaches us as the cosmic microwave background, a nearly uniform bath of microwave radiation coming from all directions. The temperature of this radiation is about 2.7 Kelvin, just a few degrees above absolute zero. It has been cooled and redshifted by the expansion of the universe. Originally, this light was emitted as visible and infrared radiation from a universe that was about 3,000 Kelvin, as hot as the surface of a red dwarf star. But over 13.8 billion years, the universe has expanded by a factor of about 1,000, and the wavelength of the light has stretched by the same factor. What was once visible light is now microwave radiation, invisible to the eye but detectable by radio telescopes and satellites. The cosmic microwave background is remarkably uniform. In every direction, it has almost exactly the same temperature. But not quite. There are tiny fluctuations, variations of only a few parts per 100,000. These fluctuations are incredibly important because they represent the seeds of all cosmic structure. Regions that were slightly denser attracted more matter, and over billions of years, these tiny density variations grew into galaxies, clusters, and the cosmic web. By studying the pattern of fluctuations in the cosmic microwave background, astronomers can learn about the early universe's composition, age, geometry, and evolution. Measurements from satellites like COBE, WMAP, and Planck have provided the most precise cosmological data we have, determining the age of the universe to within about 1%, and revealing that the cosmos is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The cosmic microwave background is also a kind of edge to our visible universe. We cannot see anything from before recombination because the universe was opaque. The cosmic microwave background is the oldest light we can observe, a glowing wall marking the limit of our view into the past. Gravitational time dilation affects everything, even GPS satellites orbiting Earth. These satellites contain extremely precise atomic clocks that broadcast timing signals to receivers on the ground. By comparing the time signals from multiple satellites, a GPS receiver can calculate its position to within a few meters. But this system only works because it accounts for relativistic effects. Each GPS satellite orbits at an altitude of about 20,000 kilometers, where Earth's gravity is weaker than at the surface. According to general relativity, clocks in weaker gravitational fields run faster than clocks in stronger fields. This causes the satellite clocks to gain about 45 microseconds per day compared to clocks on the ground. But there's another effect. The satellites are also moving at high speed, about 14,000 kilometers per hour relative to the ground. According to special relativity, moving clocks run slower than stationary ones. This causes the satellite clocks to lose about 7 microseconds per day. When you combine both effects, the satellite clocks gain a net of about 38 microseconds per day. This might not sound like much, but light travels about 30 centimeters in 1 nanosecond. In 38 microseconds, light travels about 11 kilometers. If the GPS system did not correct for these relativistic effects, position errors would accumulate at a rate of about 11 kilometers per day, and the system would become useless within hours. The fact that GPS works is a daily, practical confirmation that both special and general relativity are correct. Every time you use a navigation app on your phone, you are relying on calculations that account for the curvature of space-time and the relative passage of time in different reference frames. It is a remarkable testament to the accuracy of Einstein's theories, applied not in exotic environments like black holes, but in the mundane context of finding your way to the grocery store. The universe expands, and distant galaxies recede from us at speeds proportional to their distance. This is described by Hubble's law, which states that the velocity at which a galaxy moves away from us is equal to the Hubble constant multiplied by its distance. The current best estimate for the Hubble constant is about 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years, a galaxy is farther away. It recedes about 70 kilometers per second faster. At large enough distances, this recession velocity exceeds the speed of light. Galaxies, more than about 14 billion light-years away, in terms of their current distance accounting for expansion, are receding faster than light. This does not violate relativity because these galaxies are not moving through space faster than light. Space itself is expanding between us and them. The distinction is subtle but important. Special relativity says that nothing can move through space faster than light. But it places no limit on how fast space itself can expand. In fact, during the first fraction of a second after the Big Bang, space expanded extraordinarily fast in a period called cosmic inflation, far faster than the speed of light. This rapid expansion smoothed out the universe and set the initial conditions for structure formation. The galaxies receding faster than light are not reachable by us, even in principle. If we sent a light beam toward them today, that light would never reach them because the space between us and them is expanding faster than the light can travel. These galaxies are beyond our cosmic event horizon. We can see them now because the light we are receiving left them long ago when they were closer. But we cannot communicate with them or travel to them. They are fundamentally inaccessible, separated from us by the expansion of the universe itself. Cosmic voids are enormous regions of space that contain almost nothing. The universe's large-scale structure resembles a sponge or a web, with galaxies clustered along filaments and sheets that surround vast, empty regions. These voids can be hundreds of millions of light-years across, and they contain very few galaxies, much less than the cosmic average. The largest known void, the Boötes void, is about 330 million light-years in diameter and contains only about 60 galaxies in a volume that would normally contain thousands. Standing in the center of such a void, if you could, would be profoundly strange. The night sky would be almost empty. There would be no Milky Way, no nearby galaxies visible to the naked eye. Just a few faint smudges scattered across the darkness. Voids are not completely empty. They contain dark matter, and they have a lower density of ordinary matter as well. But compared to the dense regions where galaxies cluster, they are remarkably barren. The existence of voids is a natural consequence of gravitational collapse. In the early universe, matter was distributed almost uniformly, with tiny density fluctuations. Over billions of years, gravity amplified these fluctuations. Regions that were slightly denser attracted more matter, growing into galaxy clusters and filaments. Regions that were slightly less dense lost matter to their surroundings, becoming voids. This process created the cosmic web, a network of dense filaments separated by vast, empty regions. Voids are still expanding. As the universe continues to grow, voids get larger and emptier, while filaments and clusters continue to attract matter and grow denser. Eventually, as dark energy drives the universe's accelerated expansion, the cosmic web will be stretched even further, and the voids will dominate the universe's volume. The heat death of the universe is the ultimate fate predicted by thermodynamics, and it will take an unimaginably long time. In about 100 trillion years, the last stars will exhaust their fuel and fade. Star formation will have ceased long before that because galaxies will have run out of gas. The universe will be filled with stellar remnants, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and vast clouds of cold gas. Over even longer timescales, these remnants will slowly decay. Protons, if they are unstable as some theories suggest, will decay in about 10 to the 34 years, causing even white dwarfs and neutron stars to evaporate into radiation and lighter particles. If protons are stable, matter will still eventually collapse into black holes through random quantum tunneling events or gravitational interactions, though this will take 10 to the 65 years or longer. Black holes themselves are not eternal. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint for large black holes, but over immense timescales, it causes black holes to evaporate. A solar mass black hole will take 10 to the 67 years to evaporate. A supermassive black hole containing billions of solar masses will take 10 to the 100 years. Eventually, the universe will contain nothing but a thin soup of photons, neutrinos, and other particles, all so spread out and redshifted that their energy is negligible. The temperature of the universe will approach absolute zero. No stars will shine. No structures will exist. This is the heat death, a state of maximum entropy where no energy is available to do work and nothing can ever happen again. The universe will be dark, cold, and utterly still, expanding forever into an infinite emptiness. It is a bleak vision, but also strangely peaceful. After countless eons of activity, the cosmos will finally rest. Time itself, in a sense, will lose meaning because there will be no change, no events to mark its passage. This is the ultimate consequence of the second law of thermodynamics, applied to the universe as a whole. Entropy always increases, and eventually it reaches its maximum. Light from distant galaxies is redshifted by the expansion of space, and this redshift tells us how far away those galaxies are and how fast the universe is expanding. When light travels through expanding space, its wavelength stretches along with the expansion. Light that was originally blue or ultraviolet can be shifted all the way into the red or even infrared part of the spectrum. This is cosmological redshift, distinct from the Doppler shift caused by motion through space. The amount of redshift is expressed as a dimensionless number called z. A redshift of z equals 1 means the wavelength has doubled. A redshift of z equals 9, the highest confirmed for distant galaxies, means the wavelength has increased by a factor of 10. The light we see as near-infrared was emitted as ultraviolet. By measuring the redshift of a galaxy, astronomers can determine when the light was emitted and how far the galaxy has traveled from us due to expansion. The most distant galaxies have redshifts greater than 10, meaning we are seeing them as they appeared only a few 100 million years after the Big Bang. These galaxies are faint and difficult to observe because their light has been stretched so much that it lies in the infrared, requiring specialized telescopes like the James Webb Space Telescope to detect them. Redshift also reveals the universe's expansion rate. By comparing the redshifts of galaxies at different distances, astronomers can measure how the expansion has changed over time. This has led to the discovery that the universe's expansion is accelerating, driven by a mysterious force called dark energy. Distant supernovae appear dimmer than they should be if the universe were expanding at a constant rate, indicating that space has been expanding faster and faster over the past few billion years. Cosmological redshift affects everything. The cosmic microwave background, originally emitted as visible light, has been redshifted into the microwave part of the spectrum. Any civilization in a distant galaxy looking at our Milky Way would see it redshifted as well, its light stretched by the expansion of space. And in the far future, as the universe continues to expand and accelerate, galaxies will be redshifted so much that they fade from view entirely. Astronomers billions of years from now may see a nearly empty sky, with only their local group of gravitationally bound galaxies visible. The rest of the universe will have receded beyond the cosmic horizon, its light stretched into undetectable wavelengths. The concept of space-time is central to understanding the universe. Space and time are not separate entities, but are woven together into a single four-dimensional fabric. Events are described by 4 coordinates, 3 for space and 1 for time. The path an object takes through space-time is called its world line. Light travels along null geodesics, paths through space-time where the IA interval between events is 0. Massive objects curve space-time around them, and this curvature is what we experience as gravity. A planet orbiting a star is not being pulled by a force in the traditional sense. It is following the straightest possible path through curved space-time. Imagine space-time as a stretched rubber sheet. A massive object like a star creates a depression in the sheet. A smaller object like a planet moving near the star will naturally follow the curve of the depression orbiting the star. This is an imperfect analogy because it depicts space-time as a two-dimensional surface embedded in three-dimensional space, but it captures the essential idea. Gravity is geometry. The presence of mass and energy tells space-time how to curve, and the curvature of space-time tells objects how to move. Black holes are regions where space-time curvature becomes so extreme that it forms a one-way surface, the event horizon. Inside the horizon, all paths through space-time lead toward the singularity. It is not just hard to escape, it is geometrically impossible. Time and space swap roles inside a black hole. Outside the horizon, you can move freely through space but are always moving forward in time. Inside the horizon, moving toward the singularity is as inevitable as moving forward in time is outside. The singularity is not a place in space. It is a moment in your future, unavoidable once you cross the horizon. Understanding space-time also explains why faster-than-light travel is impossible. Moving faster than light would require traveling along a space-like path, which would mean moving backward in time in some reference frames. This leads to paradoxes, like being able to influence your own past. The structure of space-time, as described by relativity, does not permit such violations of causality. Faster-than-light travel would require exotic forms of matter with negative energy density, which may not exist in nature. Even if wormholes, theoretical shortcuts through space-time, could exist, they would likely be unstable or require exotic matter to hold them open. Space-time is the stage on which all events unfold, but it is not a passive backdrop. It is dynamic, shaped by matter and energy, rippling with gravitational waves, expanding with the universe. Understanding space-time is understanding the deepest structure of reality. Gravitational waves are ripples in space-time itself, traveling at the speed of light and carrying information about the most violent events in the universe. When two black holes spiral together and merge, they shake space-time so violently that waves radiate outward in all directions. These waves stretch and squeeze space itself as they pass. If a gravitational wave passes through you, the distance between your head and feet oscillates slightly, growing and shrinking by an amount far smaller than an atomic nucleus. This effect is incredibly tiny, but modern detectors like LIGO and Virgo can measure it. These observatories use laser interferometry to monitor the distance between mirrors separated by several kilometers. When a gravitational wave passes through, it changes the length of the arms by a distance smaller than a proton's width, and the detectors can measure this change. The first detection of gravitational waves occurred in September 2015, when LIGO observed the merger of two black holes about 30 times the mass of the Sun, located over 1 billion light-years away. The signal lasted only a fraction of a second, a chirp rising in frequency and amplitude as the black holes spiraled closer and finally merged. This detection confirmed a major prediction of general relativity and opened a new way of observing the universe. Gravitational waves carry information that light cannot. They can pass through matter without being absorbed or scattered. They reveal events that produce little or no light, like black hole mergers. They let us probe environments that are otherwise invisible, such as the interiors of neutron stars, or the moments just after the Big Bang. Since that first detection, dozens of gravitational wave events have been observed, mostly black hole mergers but also neutron star mergers. In August 2017, LIGO and Virgo detected the collision of two neutron stars. This event also produced light, gamma rays, X-rays, visible light, and radio waves, allowing astronomers to study the same event with both gravitational waves and electromagnetic radiation. This was the birth of multi-messenger astronomy. The gravitational wave background is a faint hum that fills the universe, produced by countless mergers and other events throughout cosmic history. Future detectors, like the space-based LISA mission, will be sensitive to lower-frequency gravitational waves from supermassive black hole mergers and other sources. Gravitational waves are a new sense we have gained, a way to feel the vibrations of space-time itself. Time may have had a beginning, but the question of what came before the Big Bang is perhaps unanswerable. The Big Bang was not an explosion in space. It was the beginning of space itself, and possibly the beginning of time. In the standard cosmological model, time and space emerged together at the Big Bang. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question may not have meaning because time itself did not exist before that moment. Some cosmological models suggest alternatives. In eternal inflation, our Big Bang was one of many, a bubble forming in an ever-inflating multiverse. In cyclic models, the universe goes through repeated cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch and then another Big Bang. In quantum cosmology, The universe may have tunneled into existence from nothing, a quantum fluctuation that gave rise to space, time, and matter. These ideas are speculative, and we may never know which, if any, is correct. The very early universe, in the first fraction of a second, was so hot and dense that our current understanding of physics breaks down. Quantum mechanics and general relativity, which work beautifully in their respective domains, give contradictory answers when applied to the singularity at the Big Bang. A theory of quantum gravity, which would unify these two frameworks, is needed to describe the universe's first moments. String theory, loop quantum gravity, and other approaches are being explored, but we do not yet have a complete theory. The question of time's beginning touches on philosophy as much as physics. If time had a beginning, does it make sense to ask why it began or what caused it? Causation itself is a concept embedded in time. Without time, there is no before or after, no cause preceding effect. And so we arrive at the edge of what science can address, the boundary where physics meets metaphysics. We may never have answers, but the questions themselves are beautiful. And now, let time itself begin to blur. We have drifted across billions of years, through the stretching of light and the warping of space-time. We have seen how looking outward is looking backward, how the universe expands and accelerates, how time bends near massive objects and flows differently for those who travel. We have glimpsed the cosmic microwave background, the oldest light, and pondered the heat death, the final stillness. You are floating now in the current of time, a brief flicker of awareness in a cosmos 13.8 billion years old, a universe that will continue for trillions upon trillions of years after you. But for now, you are here, resting, breathing, part of the same space-time fabric that bends around black holes and ripples with gravitational waves. Let yourself drift. The universe is patient. It has all the time in the world and more. We're traveling to worlds beyond Earth, to planets and moons scattered across our solar system and beyond. Places so strange they challenge everything we thought we knew about what a world could be. Planets where it rains glass sideways in 7,000 km/h winds. Moons with subsurface oceans that might harbor life. Worlds made of diamond, and others wrapped in methane lakes. Some of these places are closer than you think, orbiting in our own solar system. Others are light years away, circling distant stars we can barely see. But all of them remind us that Earth, for all its beauty, is just one possibility among countless others. So let your mind wander. Let your breathing slow and deepen. Let yourself drift like a spacecraft on a long, gentle trajectory through the outer solar system, past giants and ice worlds, toward the edge of everything we know. And if these cosmic journeys help you unwind, if they give you a peaceful way to end your day, consider liking and subscribing. It helps other wanderers find their way here. Now, let's begin our voyage through the strangest worlds in the universe. There is a planet made largely of carbon, and it may be covered in diamonds. 55 Cancri E orbits a sun-like star about 40 light-years away in the constellation Cancer. This planet is about twice Earth size and 8 times its mass, but what makes it extraordinary is its composition. The star it orbits is rich in carbon, and the planet appears to have formed from carbon-rich materials rather than the silicate rocks that make up Earth. Models suggest that beneath a thin atmosphere of hydrogen and helium, the planet's surface may be covered in graphite and diamond. At the extreme temperatures and pressures present on this world, carbon would crystallize into diamond rather than remaining as graphite. The surface temperature on 55 Cancri E is estimated at about 2400 degrees Celsius, hot enough to melt iron. This heat comes from its proximity to its star. The planet orbits so close that it completes one orbit in only 18 hours. One side of the planet permanently faces the star, baked in constant heat, while the other side faces eternal darkness. The temperature difference between the two hemispheres is extreme, creating powerful winds that carry heat from the day side to the night side. Some observations suggest that the planet may have volcanic activity, but instead of erupting molten rock, it might erupt with molten diamond and silicates. The surface could be a glittering, hellish landscape of crystalline mountains and rivers of liquid carbon, all shrouded in a hazy atmosphere. It sounds like something from science fiction, but the physics is sound. Under the right conditions of temperature, pressure, and chemical composition, carbon naturally forms diamonds. On Earth, diamonds form deep underground where pressure is immense. On 55 Cancri E, the entire planet may be bathed in those conditions. We will never visit this planet. It is too far away, and even if we could reach it, the conditions would be instantly lethal. But knowing it exists changes our understanding of what planets can be. They are not all rocky worlds like Earth or gas giants like Jupiter. Some are exotic, built from different elements, shaped by different processes, existing in states that seem impossible until we find them. HD 189733b is a planet where it rains glass sideways, and it represents one of the most hostile worlds ever discovered. This planet is a hot Jupiter, a gas giant that orbits extremely close to its star, completing one orbit in only 2.2 days. It is located about 63 light-years from Earth in the constellation Vulpecula. The planet's proximity to its star means its atmosphere is scorching hot, reaching temperatures of over 1,000 degrees Celsius. But what makes this world truly nightmarish is its weather. Observations using the Hubble Space Telescope revealed that the planet has a deep blue color, similar to Earth when seen from space. But this color does not come from oceans or a friendly atmosphere. It comes from silicate particles in the upper atmosphere. These particles scatter blue light, giving the planet its azure hue. The silicates are thought to condense into tiny glass particles, essentially microscopic shards of glass suspended in the atmosphere. Wind speeds on HD 189733b are measured at over 7,000 kilometers per hour, faster than the speed of sound. These winds are driven by the extreme temperature difference between the planet's day side, which faces the star, and its night side, which is slightly cooler. The planet is tidally locked, meaning the same side always faces the star, and heat is transported from day to night by ferocious atmospheric circulation. In these conditions, the glass particles are swept up by the winds and hurled sideways across the planet at hypersonic speeds. If you could somehow stand on this planet, not that there is a solid surface to stand on, you would be pelted by glass moving fast enough to vaporize anything it touched. The atmospheric pressure would crush you, the heat would incinerate you, and the glass-filled winds would shred whatever remained. It is a vision of hell, a world utterly inimical to life. Hot Jupiters like this were among the first exoplanets discovered, and they surprised astronomers. In our solar system, gas giants orbit far from the sun where it is cold. But many other star systems have gas giants in tight, scorching orbits. These planets likely formed farther out and then migrated inward over millions of years, pulled by gravitational interactions with the protoplanetary disk, or with other planets. Their existence forced scientists to rethink theories of planetary formation and migration. PSRJ 1719-1438b is another diamond planet, but this one is even stranger because it orbits a pulsar. Pulsars are rapidly rotating neutron stars that emit beams of radiation. This particular pulsar is located about 4,000 light-years away in the constellation Serpens, and it spins 363 times per second. Orbiting the pulsar is a planet, or more accurately, the remains of a star. The planet is about 5 times the mass of Jupiter, but it is incredibly dense and composed almost entirely of crystallized carbon. Astronomers believe this planet is the remnant of a white dwarf star. The pulsar and the white dwarf were once a binary system. Over time, the pulsar's intense gravity and radiation stripped away the outer layers of the white dwarf, leaving only its dense carbon core. This core, under immense pressure, crystallized into diamond. The result is a planet-sized diamond orbiting a dead star. The orbit is extremely close, only about 600,000 kilometers, closer than the Moon is to Earth. The pulsar's radiation bathes the diamond planet in high-energy particles and light. From the surface of the planet, if you could stand on a diamond that size, the pulsar would appear as a brilliant, pulsing beacon, flashing hundreds of times per second. The sky would be filled with radiation, and the gravitational field would be immense. This system is a graveyard, the remnants of 2 stars that lived, died, and left behind something beautiful and strange. It is also a reminder that planets are not always born from protoplanetary disks. They can be created in the aftermath of stellar death, forged from the cores of consumed stars. Titan is Saturn's largest moon, and it is the only moon in the solar system with a thick atmosphere and stable liquids on its surface. But these are not oceans of water. Titan is too cold for that. With surface temperatures around minus 179 degrees Celsius, water ice is as hard as rock. Instead, Titan's lakes and seas are filled with liquid methane and ethane. Titan has a complete hydrological cycle, but instead of water, it cycles methane. Methane evaporates from the lakes, rises into the atmosphere, condenses into clouds, and falls back to the surface as rain. Methane rivers carve channels through the icy landscape, flowing into vast lakes near the poles. The largest of these, Kraken Mare, is bigger than the Caspian Sea on Earth. Radar observations from the Cassini spacecraft mapped Titan's surface in detail, revealing a world shaped by familiar processes but operating with alien chemistry. There are mountains, valleys, and dunes. The dunes are made not of silicate sand, but of organic particles. Complex hydrocarbons created by sunlight breaking apart methane in the upper atmosphere. These particles drift down and accumulate into vast dune fields near the equator, sculpted by Titan's gentle winds. Titan's thick atmosphere is mostly nitrogen, like Earth's, but with significant amounts of methane and traces of other hydrocarbons. The atmospheric pressure at the surface is about 50% higher than Earth's at sea level. The sky is a perpetual orange haze, created by smog-like aerosols. Sunlight is dim, only about 1% as bright as on Earth, because Titan is 10 times farther from the Sun. Despite the cold and the alien chemistry, Titan is considered one of the most promising places in the solar system to search for life. Its subsurface ocean, a layer of liquid water mixed with ammonia beneath the icy crust, might harbor microbial life. And some scientists speculate that life based on different chemistry, using liquid methane as a solvent instead of water, might exist in Titan's surface lakes. It is pure speculation, but Titan has the complex organic chemistry and energy sources that life might exploit. Future missions, possibly including a submarine to explore Kraken Mare, could search for signs of life in this strange, distant world. Europa is one of Jupiter's 4 large moons, and beneath its icy surface lies an ocean that contains more water than all of Earth's oceans combined. Europa's surface is a smooth shell of ice, crisscrossed, with reddish-brown streaks and cracks. The ice is estimated to be 15 to 25 kilometers thick, and beneath it is a global ocean perhaps 100 kilometers deep. This ocean is kept liquid by tidal heating. Europa orbits Jupiter in an elliptical path, and as it moves closer and farther from the giant planet, Jupiter's gravity flexes and squeezes the moon. This constant kneading generates heat through friction, enough to keep the subsurface ocean from freezing despite being far from the sun. The surface of Europa is one of the smoothest in the solar system, with very few impact craters. This suggests the surface is geologically young, constantly renewed by ice rising from below or liquid water erupting from beneath. Some regions show chaotic terrain, where the ice has broken apart, shifted, and refrozen, like pack ice on Earth's polar seas. Observations from the Hubble Space Telescope and the Galileo spacecraft suggest that Europa may have water plumes erupting from its surface, shooting up to 200 kilometers into space before falling back down. These plumes may come from cracks in the ice where the ocean below is exposed. If this is true, a spacecraft could fly through these plumes and analyze the water directly, searching for organic molecules or other signs of life without having to drill through the ice. Europa's ocean is one of the most promising places in the solar system to look for extraterrestrial life. The ocean is in contact with a rocky seafloor, which means there could be hydrothermal vents, underwater volcanoes where heat and chemicals provide energy for life. On Earth, hydrothermal vents support rich ecosystems that do not rely on sunlight. Life around these vents uses chemical energy from the hot, mineral-rich water. Europa's ocean might have similar systems. NASA is planning a mission called Europa Clipper, which will orbit Jupiter and make dozens of close flybys of Europa, studying its ice shell, ocean, and potential plumes. The goal is to determine whether Europa has the conditions necessary for life. If it does, a future mission might land on the surface, drill through the ice, and explore the ocean below. It would be one of the most ambitious explorations ever attempted. Venus rotates backwards compared to most planets, and a day on Venus is longer than a year. Venus is Earth's closest planetary neighbor and similar in size, but it could not be more different in character. The surface temperature is about 470 degrees Celsius, hot enough to melt lead, and the atmospheric pressure is 90 times that of Earth, equivalent to being a kilometer underwater. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid, and it rains acid that evaporates before reaching the ground. But one of the strangest things about Venus is its rotation. Most planets rotate counterclockwise when viewed from above their north pole, the same direction they orbit the Sun. Venus rotates clockwise. It is the only planet in the solar system with retrograde rotation. We do not know why. One possibility is that Venus originally rotated like the other planets, but a massive collision early in its history flipped it over. Another idea is that gravitational interactions with the Sun and tidal effects in its thick atmosphere gradually slowed and reversed its rotation over billions of years. Venus rotates extremely slowly. It takes 243 Earth days to complete one rotation, but it only takes 225 Earth days to orbit the Sun. This means a day on Venus, one full rotation, is longer than a Venusian year. If you stood on the surface, the Sun would rise in the west and set in the east, and it would take nearly 117 Earth days to go from sunrise to sunset. The slow rotation and thick atmosphere create strange weather patterns. Winds in the upper atmosphere reach speeds of up to 360 kilometers per hour, circling the planet in only 4 Earth days. This phenomenon, called superrotation, is not fully understood. The winds are much faster than the planet's surface rotates, driven by complex interactions between solar heating and atmospheric dynamics. Venus is often called Earth's twin because of its similar size and composition, but it is a cautionary tale. Venus likely had liquid water oceans billions of years ago, but a runaway greenhouse effect boiled them away. Carbon dioxide accumulated in the atmosphere, trapping heat and raising temperatures until the surface became the inferno it is today. Understanding Venus helps us understand Earth's climate and the risks of unchecked greenhouse gas emissions. Triton is Neptune's largest moon, and it is the only large moon in the solar system that orbits in the opposite direction to its planet's rotation. Triton's retrograde orbit is strong evidence that it did not form alongside Neptune. Instead, it was likely a dwarf planet from the Kuiper Belt, captured by Neptune's gravity billions of years ago. This capture would have been a violent event, disrupting Triton's original orbit and heating its interior through tidal forces. Over time, its orbit became more circular, but it remains retrograde. Triton is geologically active despite being one of the coldest objects in the solar system, with surface temperatures around minus 235 degrees Celsius. Voyager 2, the only spacecraft to visit Neptune, discovered active geysers on Triton's surface. These geysers erupt with nitrogen gas and ice particles, shooting plumes up to 8 kilometers high. The nitrogen is warmed by sunlight penetrating Triton's thin, translucent ice cap, causing it to sublimate and burst through weak points in the surface. Triton's surface is young and varied, with cantaloupe terrain, strange pitted and ridged areas unlike anything else in the solar system. There are also smooth plains, frozen lakes of nitrogen and methane, and long fractures where icy material has welled up from below. The moon's pinkish color comes from methane ice and organic compounds created by radiation. Triton's fate is sealed. Because its orbit is retrograde, tidal forces are slowly pulling it closer to Neptune. In about 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome the moon's own gravity. When this happens, Triton will be torn apart, and its fragments will form a spectacular ring system around Neptune, far more impressive than the faint rings that exist today. For now, Triton remains intact, a captured wanderer slowly spiraling toward its destruction, one of the most dynamic and doomed moons in the solar system. Pluto may no longer be classified as a planet, but it is no less fascinating. Its most famous feature is a heart-shaped plain called Sputnik Planitia, a vast expanse of nitrogen ice about 1,000 kilometers across. This plain is remarkably smooth, free of impact craters, which means it is geologically young, constantly renewed by processes happening beneath the surface. Sputnik Planitia sits in a large impact basin, and its surface is divided into polygonal cells, each tens of kilometers wide. These cells are created by convection. Nitrogen ice, warmed slightly by heat from Pluto's interior, becomes buoyant and rises. At the surface, it cools, spreads outward, and sinks back down at the cell boundaries. This convection cycle takes about 500,000 years to complete, an incredibly slow churn that constantly resurfaces the plane. The nitrogen ice in Sputnik Planitia is several kilometers thick, and it acts like a glacier, flowing and deforming under its own weight. Some of the nitrogen sublimates, turning directly from ice to gas during Pluto's brief summer, and then refreezes during winter. This creates seasonal cycles of sublimation and deposition that shape the landscape. Pluto has a thin atmosphere made mostly of nitrogen with traces of methane and carbon monoxide. As Pluto orbits the Sun in its elliptical, 248-year orbit, its distance from the Sun changes dramatically. When Pluto is closest to the Sun, more ice sublimates, thickening the atmosphere. When it moves farther away, the atmosphere begins to freeze and fall back to the surface as snow. Pluto also has mountains made of water ice, which at Pluto's temperatures is as hard and strong as rock. Some of these mountains are several kilometers high, standing at the edge of Sputnik Planitia like coastal ranges. They are thought to be fragments of Pluto's water ice crust, floating in the denser nitrogen ice like icebergs. Pluto's large moon, Charon, is so big relative to Pluto that the two are sometimes considered a binary system. They are tidally locked, always showing the same face to each other, orbiting a point in space between them. The New Horizons spacecraft, which flew past Pluto in 2015, revealed a world far more complex and active than anyone expected, a small, distant world still shaping its surface billions of years after its formation. Enceladus is one of Saturn's smaller moons, only about 500 kilometers across, but it is one of the most exciting places in the solar system for astrobiology. Enceladus has a subsurface ocean beneath an icy crust, and it erupts with geysers that shoot water, ice particles, and organic molecules into space. These geysers emerge from long fractures near the Moon's south pole called tiger stripes. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition. The plumes contain water vapor, ice grains, salts, silica particles, and organic compounds including methane and complex carbon molecules. The presence of salts and silica indicates that the ocean is in contact with a rocky core, and the water is likely interacting with hot rock, similar to hydrothermal vents on Earth. The heat that keeps Enceladus's ocean liquid comes from tidal heating, the same process that warms Europa. Enceladus orbits Saturn in an elliptical path, and Saturn's gravity flexes the Moon, generating internal friction and heat. The south polar region is the warmest part of Enceladus, with temperatures reaching about minus 120 degrees Celsius, much warmer than the rest of the surface. The ocean itself may be quite warm near the rocky core, possibly heated to temperatures where life could thrive. The presence of organic molecules and chemical energy sources makes Enceladus a prime candidate for hosting microbial life. Some scientists argue that Enceladus is the best place in the solar system to search for extraterrestrial life because the ocean material is being ejected into space, making it accessible without having to drill through the ice. A future mission could carry more sophisticated instruments through the plumes, specifically designed to detect biosignatures like amino acids, lipids, or even microbial cells. Enceladus reminds us that life might exist in hidden oceans throughout the solar system, beneath the surfaces of moons we once thought were frozen and dead. Jupiter's Great Red Spot is the largest storm in the solar system, a massive anticyclonic hurricane that has been raging for at least 350 years, and possibly much longer. Early telescopic observations in the 1600s may have recorded it, though the historical record is unclear. The storm is enormous, currently about 16,000 kilometers wide, large enough to swallow Earth. It used to be even bigger. Observations over the past century show that the Great Red Spot has been shrinking, though the reason is not well understood. The storm rotates counterclockwise, completing one rotation every 6 to 7 days. Wind speeds at the edge reach up to 680 kilometers per hour. The storm's reddish color comes from complex organic molecules and phosphorus compounds brought up from deeper in Jupiter's atmosphere and altered by ultraviolet light from the sun. The exact chemistry is still debated. Jupiter's atmosphere is divided into bands of clouds moving at different speeds. The Great Red Spot sits between two of these bands, and the shearing winds help sustain the storm. Unlike hurricanes on Earth, which lose energy when they move over land or cold water, Jupiter's storms have no solid surface to disrupt them. They can persist for centuries, fed by Jupiter's internal heat and the planet's rapid rotation, which completes one day in less than 10 hours. Other storms exist on Jupiter as well, including smaller white and brown ovals, but none match the Great Red Spot's size or longevity. The Juno spacecraft, currently orbiting Jupiter, has provided unprecedented views of the storm, imaging it from above and using microwave instruments to peer beneath the cloud tops. These observations reveal that the storm extends deep into the atmosphere, at least 300 kilometers down, far deeper than previously thought. The Great Red Spot is slowly shrinking and may eventually dissipate, but for now, it remains one of the solar system's most iconic features, a testament to the power and persistence of planetary atmospheres. There are exoplanets called hot Neptunes, worlds similar in size to Neptune but orbiting close to their stars. GJ 3470b is one example, orbiting a red dwarf star 57 light-years away. These planets have thick atmospheres of hydrogen and helium, but the intense radiation from their nearby stars can strip away the lighter elements over time. Some hot Neptunes may be in the process of losing their atmospheres, shrinking into rocky super-Earths. Others have atmospheres enriched with heavier molecules like water vapor and methane. Studying these worlds helps astronomers understand atmospheric escape and planetary evolution. There are also super-Earths, rocky planets larger than Earth but smaller than Neptune. Kepler 452b is a super-Earth located in its star's habitable zone, the region where liquid water could exist on the surface. It orbits a Sun-like star 1,400 light-years away and is about 60% larger than Earth. Its year is 385 days, remarkably similar to our own. We do not know if it has an atmosphere or liquid water, but its size and location make it one of the most potentially habitable exoplanets discovered. If it has a thick atmosphere and a magnetic field, it could have oceans and perhaps life. We will not know for certain until more powerful telescopes can analyze its atmosphere, searching for water vapor, oxygen, and other biosignatures. The diversity of exoplanets is staggering. There are lava worlds with surfaces hot enough to vaporize rock, ice giants with diamond rain in their interiors, rogue planets drifting through interstellar space with no star at all, planets orbiting binary stars where two suns rise and set. Each discovery expands our understanding of what planets can be and where life might arise. And now, let the alien skies begin to fade. We have traveled across the solar system and beyond, from the diamond planets circling dead stars to the methane lakes of Titan, from the subsurface oceans of Europa and Enceladus to the hellish winds of glass-raining worlds. We have seen storms that rage for centuries and moons spiraling toward their doom. These worlds are real. They exist right now, spinning in the darkness, shaped by forces we are only beginning to understand. And somewhere among them, perhaps in an ocean beneath the ice or in a temperate zone around a distant star, life may have found a way. You are resting now, floating in thought between worlds, a traveler in your mind across the cosmos. Let the strangeness comfort you. Let the vastness cradle you. The universe is full of wonders, and tomorrow they will still be there, waiting. We're venturing into the deepest mysteries of the cosmos, the questions that keep scientists awake at night, the phenomena we can detect but cannot explain, the gaps in our understanding that reveal just how much we still have to learn. Dark matter that holds galaxies together but remains invisible. Dark energy pushing the universe apart at an accelerating pace. The silence of a cosmos that should be teeming with life but shows no signs of other civilizations. These are not failures of science. They are invitations, reminders that the universe is far stranger and more mysterious than we ever imagined. So settle in one last time. Let your breathing slow and deepen. Let your thoughts drift like signals traveling through the cosmic void, searching for answers in the darkness. And if these journeys have brought you peace, consider subscribing so others can find their way here too. Now, let's begin with the invisible scaffolding that holds everything together. Dark matter makes up 85% of all matter in the universe, yet we have never directly detected a single particle of it. We know dark matter exists because of its gravitational effects. Galaxies rotate too fast. Based on the visible matter alone, stars, gas, and dust, the outer edges of galaxies should be moving slowly, following the same orbital mechanics that govern planets around the Sun. But observations show that stars in the outer regions of galaxies move just as fast as those near the center, as if the galaxy were rotating like a solid disk rather than a collection of objects orbiting a central mass. The only explanation is that galaxies are embedded in massive halos of invisible matter, matter that exerts gravity but does not emit, absorb, or reflect light. This dark matter outweighs all the visible matter in a galaxy by a factor of about 5 to 1. The evidence for dark matter extends beyond individual galaxies. Galaxy clusters, the largest gravitationally bound structures in the universe, contain hot gas that emits X-rays. By measuring the temperature and distribution of this gas, astronomers can calculate how much mass is needed to hold the cluster together. The answer is always far more than the visible matter can account for. Dark matter is also revealed through gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of that object bends the light, distorting the image of the background galaxy. By studying these distortions, astronomers can map the distribution of mass in the foreground cluster, and the maps consistently show that most of the mass is dark matter, distributed in a smooth halo around the visible galaxies. The cosmic microwave background, the afterglow of the Big Bang, also provides evidence for dark matter. Tiny fluctuations in the temperature of this radiation reflect density variations in the early universe. The pattern of these fluctuations depends on the universe's composition, and the data fits perfectly with a universe made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Despite all this evidence, we do not know what dark matter is. It cannot be ordinary matter like atoms and molecules because ordinary matter interacts with light. Dark matter must be made of something else. Particles that interact only through gravity and possibly through the weak nuclear force. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles predicted by some extensions of the standard model of particle physics. Experiments deep underground and in space have searched for WIMPs by looking for rare interactions with ordinary matter, but so far none have been detected. Another candidate is axions, extremely light particles that were proposed to solve a problem in quantum chromodynamics. Axions would be produced in vast numbers in the early universe and could clump together to form the dark matter halos we observe. Other proposals include primordial black holes, small black holes formed in the first moments after the Big Bang, or sterile neutrinos, hypothetical cousins of ordinary neutrinos that do not interact through the weak force. The mystery of dark matter is one of the most important unsolved problems in physics. It tells us that the standard model, our best theory of particle physics, is incomplete. There are particles and forces we have not yet discovered, and understanding dark matter will require new physics, new experiments, and perhaps entirely new ways of thinking about the universe. Dark energy is even more mysterious than dark matter, and it makes up 68% of the total energy content of the universe. Dark energy is the name given to whatever is causing the universe's expansion to accelerate. For most of cosmic history, the expansion of the universe was slowing down due to the gravitational attraction of matter pulling everything together. But about 5 billion years ago, something changed. The expansion began to speed up. Galaxies are now moving away from each other faster and faster, and this acceleration is driven by dark energy. The discovery of dark energy came from observations of distant supernovae in the late 1990s. Type Ia supernovae are useful as standard candles because they have a consistent peak brightness. By measuring how bright a supernova appears and comparing it to how bright it should be, astronomers can determine its distance. When researchers measured the distances to supernovae in galaxies billions of light years away, they found that those supernovae were dimmer than expected. This meant the galaxies were farther away than predicted by a universe expanding at a constant rate. The only explanation was that the universe's expansion had accelerated, pushing those galaxies farther away than they would be in a decelerating universe. This discovery was shocking and earned the Nobel Prize in Physics in 2011. Dark energy behaves like a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This is unlike matter and radiation, which become more dilute as the universe grows. Dark energy maintains a constant density, and as the volume of the universe increases, the total amount of dark energy increases as well. The simplest explanation for dark energy is the cosmological constant, a term that Einstein introduced into his equations of general relativity. Einstein originally added this term to allow for a static universe, but he later called it his greatest blunder when observations showed the universe was expanding. Ironically, the cosmological constant may have been correct after all, not as a way to balance gravity and keep the universe static, but as a representation of the energy of empty space itself. Quantum field theory predicts that empty space is not truly empty. It seethes with virtual particles that pop in and out of existence, and this vacuum energy should exert a repulsive gravitational effect. The problem is that when physicists calculate the expected value of vacuum energy using quantum mechanics, they get an answer that is about 10 to the 120 times larger than the observed value of dark energy. This is called the cosmological constant problem, and it is one of the worst mismatches between theory and observation in all of science. Some physicists propose that dark energy is not constant, but changes over time, a scenario called quintessence. Others suggest modifications to general relativity on cosmic scales. But so far, all observations are consistent with a simple cosmological constant. Dark energy dominates the universe's future. As expansion accelerates, distant galaxies will recede beyond the cosmic horizon, their light red shifted into invisibility. In trillions of years, observers in our local group of galaxies will see an empty universe, with only the gravitationally bound galaxies nearby visible. The rest of the cosmos will have disappeared beyond reach, carried away by the relentless expansion driven by dark energy. The Fermi paradox asks one of the most profound questions in science. If the universe is so vast and contains billions of potentially habitable planets, where is everyone? The paradox is named after physicist Enrico Fermi, who reportedly asked this question during a lunch conversation in 1950. The reasoning is straightforward. Our galaxy contains over 100 billion stars, and many of those stars have planets. Recent discoveries by telescopes like Kepler have shown that planets are common, and many orbit in the habitable zone where liquid water could exist. Even if only a tiny fraction of planets develop life, and only a tiny fraction of those develop intelligent life, and only a tiny fraction of those develop technology, there should still be thousands or millions of technological civilizations in the Milky Way. Our galaxy is about 13 billion years old, and the Sun is relatively young, only 4.6 billion years old. Other star systems are much older, giving life billions of additional years to evolve and develop technology. If even one civilization had developed interstellar travel and started colonizing other star systems, it could spread across the entire galaxy in just a few million years, a blink of an eye in cosmic time. So, where are they? Why haven't we detected any radio signals, spacecraft, or other signs of extraterrestrial intelligence? This is the Fermi paradox. Many solutions have been proposed. Perhaps intelligent life is extremely rare. Perhaps the development of technology is a rare event. Perhaps civilizations destroy themselves shortly after developing advanced technology, through nuclear war, environmental collapse, or some other catastrophe. This is sometimes called the Great Filter, a barrier that prevents civilizations from reaching a spacefaring stage. If the Great Filter is behind us, in our past, then we are incredibly lucky to have made it this far. If the Great Filter is ahead of us, in our future, then our prospects are grim. Perhaps advanced civilizations exist but choose not to communicate or expand. They might follow a policy of non-interference, observing but not contacting less advanced species. Or perhaps they communicate in ways we cannot detect, using technologies or methods we have not yet imagined. Perhaps interstellar travel is simply too difficult. The distances between stars are enormous, and even traveling at a significant fraction of the speed of light would require energy resources far beyond what we can currently imagine. Civilizations might exist on their homeworlds but remain isolated by the sheer vastness of space. Perhaps we are simply not looking in the right way or in the right places. Our searches for extraterrestrial intelligence have been limited in scope, focusing primarily on radio signals from nearby stars. The universe is vast, and we have only just begun to explore it. Another possibility is that we are alone. Perhaps the sequence of events that led to intelligent life on Earth was so improbable that it has not happened anywhere else in the observable universe. This is a lonely and humbling thought, but it is consistent with the evidence we have. The Fermi paradox remains unresolved. It challenges our assumptions about life, intelligence, and our place in the cosmos. It reminds us that despite our scientific progress, we still do not understand one of the most basic questions: are we alone? The cosmological constant problem is one of the deepest puzzles in theoretical physics, revealing a profound disconnect between quantum mechanics and general relativity. Quantum field theory, the framework that describes the behavior of particles and forces at the smallest scales, predicts that empty space is not truly empty. The vacuum is filled with fields, and these fields fluctuate due to the Heisenberg uncertainty principle. Particles and antiparticles constantly pop into and out of existence in a roiling quantum foam. These virtual particles should contribute to the energy of the vacuum, and since energy and mass are equivalent through Einstein's equation E equals mc squared, this vacuum energy should gravitate. It should affect the expansion of the universe. When physicists calculate the expected vacuum energy using quantum field theory, they sum up the contributions from all possible particle interactions at all possible energy scales. The result is an absurdly large number, about 10 to the 113 joules per cubic meter. This energy should act as a cosmological constant, driving the universe's expansion at an enormous rate. But observations show that the actual vacuum energy, the dark energy that drives cosmic acceleration, is about 10 to the minus 9 joules per cubic meter, a difference of 122 orders of magnitude. This is not just a small discrepancy. It is the worst prediction in the history of physics. Something is wrong with our understanding, but we do not know what. One possibility is that there is a mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe. But no one has found a satisfactory mechanism. Supersymmetry, a proposed extension of the Standard Model, could provide such a cancellation, but supersymmetry has not been detected despite extensive searches at particle accelerators. Another approach invokes the anthropic principle. Perhaps the vacuum energy can take on different values in different regions of space or in different universes within a multiverse. In most regions, the vacuum energy is so large that it either causes the universe to expand so rapidly that galaxies never form, or it causes the universe to collapse immediately. Only in regions where the vacuum energy happens to be very small can galaxies, stars, and life develop. We find ourselves in such a region not because it is typical, but because it is the only type of region where observers can exist. This explanation is unsatisfying to many physicists because it gives up on finding a fundamental reason for the value of the vacuum energy. It suggests that the value is an accident, a random feature of our particular patch of the multiverse. But without a better explanation, the anthropic principle remains on the table. The cosmological constant problem is a sign that our current theories are incomplete. General relativity works beautifully on large scales, and quantum mechanics works beautifully on small scales, but we do not have a theory that unifies them. A theory of quantum gravity, which would describe how spacetime itself behaves at the quantum level, is needed to resolve the cosmological constant problem. String theory, loop quantum gravity, and other approaches are being explored, but we are still far from a complete understanding. The matter-antimatter asymmetry is another profound mystery. According to the laws of physics as we understand them, matter and antimatter should have been created in equal amounts during the Big Bang. Every particle of matter, an electron, a proton, a neutron, has a corresponding antiparticle with the same mass but opposite charge. When a particle meets its antiparticle, they annihilate, converting their mass into energy in the form of photons. In the early universe, temperatures were so high that particles and antiparticles were constantly being created and destroyed. As the universe cooled, the production of new particles slowed, and most of the existing particles and antiparticles annihilated each other. If matter and antimatter had been created in exactly equal amounts, they should have annihilated completely, leaving behind only photons. The universe should contain no matter at all, just light and other forms of radiation. But clearly, that is not what happened. We exist. The stars, galaxies, and planets exist. Observations of the cosmic microwave background show that for every billion matter-antimatter pairs in the early universe, there was one extra particle of matter. This tiny asymmetry, 1 part in a billion, is the reason the universe contains matter today. All the matter we see, everything made of atoms, comes from that small excess. But why was there an asymmetry? What caused matter to outnumber antimatter? This is one of the great unsolved problems in cosmology. The standard model of particle physics allows for a small amount of matter-antimatter asymmetry through processes involving the weak nuclear force, but the effect is far too small to explain the observed imbalance. Something else must have happened in the early universe to create the excess of matter. One possibility is that there are undiscovered particles or forces that violate the symmetry between matter and antimatter more strongly than the known particles do. Grand, unified theories and theories of quantum gravity often predict such violations. Another possibility is that the asymmetry was generated during a phase transition in the early universe, a moment when the laws of physics changed as the universe cooled. Some theories propose that the excess matter was created through the decay of heavy particles that interacted differently with matter and antimatter. Experiments at particle accelerators like the Large Hadron Collider are searching for clues by studying the behavior of particles containing bottom quarks and other exotic particles. Observations of the cosmic microwave background and the distribution of elements in the universe also provide constraints. But so far, we do not have a definitive answer. The matter-antimatter asymmetry is a reminder that the universe's history contains events we do not fully understand, processes that shaped the cosmos in its first moments and determined everything that followed. The Great Filter is a concept that attempts to explain the Fermi paradox by proposing that there is a barrier, or filter, that prevents life from becoming a space-faring, galaxy-spanning civilization. The filter could lie in our past, in which case we have already passed it and are among the rare civilizations that made it through. Or it could lie in our future, in which case our prospects for long-term survival are grim. If the Great Filter is in the past, it might be the emergence of life itself. Perhaps the transition from non-living chemistry to self-replicating organisms is so improbable that it has only happened once or a few times in the observable universe. Or perhaps the filter is the development of complex cells, On Earth, it took about 2 billion years for simple prokaryotic cells to evolve into complex eukaryotic cells with nuclei and organelles. This transition might be extremely rare. Another possibility is the emergence of intelligence. Evolution does not inevitably lead to intelligence. On Earth, intelligent tool-using species have only evolved once in over 3 billion years of complex life. Perhaps intelligence is a rare outcome, a fluke of evolution rather than a common endpoint. If the great filter is in our future, the implications are disturbing. It would suggest that something prevents civilizations from surviving long after they develop technology. This could be self-destruction through nuclear war, biological weapons, or environmental collapse. It could be the misuse of advanced technologies like artificial intelligence or nanotechnology. Or it could be something we have not yet imagined, a danger that only becomes apparent once a civilization reaches a certain level of advancement. Some researchers argue that the fact that we have not detected any signs of extraterrestrial civilizations is evidence that the great filter lies ahead. If intelligent life were common and typically survived to become spacefaring, we should see evidence of their presence, megastructures, radio signals, or artifacts. The silence suggests that something prevents civilizations from reaching that stage. Others argue that the filter could be the transition to a spacefaring species itself. Perhaps the technical challenges and resource requirements of interstellar travel are so immense that no civilization has managed to do it. Or perhaps civilizations lose interest in expansion and choose to focus on virtual realities, artificial worlds, or other pursuits. The Great Filter hypothesis does not provide answers. It is a framework for thinking about the Fermi paradox, a way to organize the possible explanations. But it highlights a sobering possibility. If the filter is ahead of us, then the future of humanity may be far more fragile than we imagine. Cosmic inflation is the theory that the universe underwent a period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang. But we do not fully understand what caused it or what it means for the nature of reality. In the standard Big Bang model, the universe began in a hot, dense state and has been expanding ever since. But this model has some problems. One is the horizon problem. The cosmic microwave background has almost exactly the same temperature in all directions. But, according to the standard model, regions on opposite sides of the sky were never in contact with each other. They were too far apart for light to travel between them in the time since the Big Bang. So, how did they end up at the same temperature? Another problem is the flatness problem. The universe appears to be geometrically flat, meaning that parallel lines never converge or diverge. But a flat universe is an unstable state. Any deviation from perfect flatness should grow over time, and the early universe should have been either extremely curved or required an incredibly precise fine-tuning of initial conditions. Cosmic inflation solves these problems by proposing that the universe underwent a brief period of exponential expansion in the first tiny fraction of a second, around 10 to the minus 36 seconds after the Big Bang. During this period, the universe expanded by a factor of at least 10 to the 26, possibly much more. This expansion was driven by a field called the inflaton field, which had a high energy density and negative pressure. This negative pressure acts like anti-gravity, causing space itself to expand at an accelerating rate. Inflation stretches the universe so much that regions that were initially in contact, and thus at the same temperature, are pulled far apart. This explains why the cosmic microwave background is so uniform. It also flattens the geometry of the universe, just as inflating a balloon makes its surface appear flatter. After inflation ended, the energy of the inflated field was converted into ordinary matter and radiation, reheating the universe and beginning the hot Big Bang phase we normally think of. Inflation also explains the origin of structure in the universe. Quantum fluctuations in the inflated field were stretched to cosmic scales during inflation, creating tiny density variations. These variations became the seeds of galaxies and galaxy clusters. The pattern of fluctuations predicted by inflation matches the pattern observed in the cosmic microwave background with remarkable precision. But we do not know what the inflated field is or why it behaved the way it did. Inflation is a compelling idea that solves several problems and makes predictions that have been confirmed, but it is not yet a complete theory. Some versions of inflation predict that it never truly ends. In most regions of space, inflation continues forever, but in some regions, it stops and a bubble universe forms. Our universe is one such bubble, and there may be countless others, each with different physical laws and constants. This is the idea of eternal inflation and the multiverse, and it is deeply controversial because it may be impossible to test. The black hole information paradox reveals a conflict between quantum mechanics and general relativity, and it has puzzled physicists for decades. According to quantum mechanics, information cannot be destroyed. If you know the complete quantum state of a system at one moment, you can, in principle, calculate its state at any future moment. Information is conserved, but black holes seem to violate this rule. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe. The information about what fell in, its composition, its quantum state, seems to disappear. Even worse, Stephen Hawking showed in the 1970s that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate over immense timescales. Eventually, the black hole disappears completely. If the radiation is random and carries no information about what fell in, then the information is truly destroyed, violating the principles of quantum mechanics. This is the information paradox. Some physicists argue that information is not destroyed, but is somehow encoded in the Hawking radiation or stored in the event horizon itself. The holographic principle suggests that all the information about the volume of space can be encoded on a boundary surface, like a hologram. Applied to black holes, this means the event horizon contains all the information about what fell in, and this information is released as the black hole evaporates. Others propose that information is preserved in a remnant left behind when the black hole evaporates, or that it escapes into another universe through a wormhole connected to the black hole's interior. Recent work suggests that information is not lost, but is scrambled in extremely complex ways, encoded in subtle correlations in the Hawking radiation. This would preserve quantum mechanics, but requires a deep connection between the black hole's interior and exterior that we do not fully understand. The information paradox is not just a puzzle about black holes. It is a sign that our understanding of space-time, quantum mechanics, and gravity is incomplete. Resolving the paradox will likely require a theory of quantum gravity that unifies these concepts. The Hubble tension is a recent and puzzling discrepancy in cosmology. The Hubble constant describes how fast the universe is expanding, and it can be measured in two different ways. One method uses observations of the cosmic microwave background. By studying the pattern of fluctuations in this ancient light and using our understanding of the early universe, cosmologists can calculate what the expansion rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. The other method uses observations of nearby objects like Cepheid variable stars and type Ia supernovae. These objects act as distance markers, allowing astronomers to measure how fast galaxies are moving away from us. This method gives a value of about 73 kilometers per second per megaparsec. The difference might not sound like much, but it is statistically significant. The two measurements disagree by more than the uncertainties in the data. This is the Hubble tension, and it suggests that something is wrong with our understanding of the universe. One possibility is that there are systematic errors in one or both measurements. Perhaps the distance ladder used to calibrate nearby supernovae is slightly off, or perhaps our model of the early universe is missing something. But extensive checks have not found any obvious errors. Another possibility is that the universe's expansion has changed in unexpected ways. Perhaps there is a new form of energy or a new interaction that affects the expansion rate. Or perhaps general relativity needs to be modified on cosmological scales. Some researchers propose that the tension could be resolved by early dark energy, a form of energy that existed in the early universe but has since faded away. Others suggest variations in the strength of gravity or changes in the properties of neutrinos. The Hubble tension is a reminder that even in well-established fields like cosmology, surprises can emerge. It may be a clue pointing toward new physics, or it may be resolved by better measurements and improved models. Either way, it is one of the most active areas of research in cosmology today. Oumuamua is the first known interstellar object to pass through our solar system, and its behavior was strange enough to spark intense debate. Oumuamua, a Hawaiian word meaning scout or messenger, was discovered in October 2017 by the Pan-STARRS telescope in Hawaii. It was moving too fast to be bound to the Sun, confirming that it came from another star system. Oumuamua was small, elongated, and tumbling chaotically. Observations suggested it was cigar-shaped or possibly disc-shaped, with a length of about 400 meters and a width of only 40 meters. Its surface was reddish, similar to objects in the outer solar system that have been bombarded by cosmic rays for millions of years. But the strangest thing about Oumuamua was its motion. As it passed the Sun and began moving back into interstellar space, it accelerated slightly, more than could be explained by the Sun's gravity alone. Comets often show such non-gravitational acceleration because they release gas and dust as they are heated by the Sun, and this outgassing acts like a rocket. But Oumuamua showed no signs of a tail or coma, no visible outgassing. So what was pushing it? Several explanations were proposed. Perhaps Oumuamua was releasing gas in amounts too small to detect visually, but enough to cause the acceleration. Perhaps it was made of pure hydrogen ice, which would sublimate without leaving a visible trail. Perhaps it was an unusual type of comet, or a fragment of a planet shattered by tidal forces. One scientist, Avi Loeb from Harvard, suggested that Oumuamua could be an artificial object, perhaps a light sail built by an extraterrestrial civilization. A light sail is a thin reflective sheet pushed by sunlight, and such an object would experience acceleration without outgassing. This proposal was controversial and rejected by most astronomers, who argued that natural explanations were more plausible. But the debate highlighted how little we know about interstellar objects. Oumuamua passed through the solar system quickly, and by the time its strange behavior was noticed, it was already too far away for detailed study. It is now beyond the reach of our telescopes, continuing its journey through the galaxy. Since Oumuamua, a second interstellar object, comet Borisov, was discovered in 2019. Borisov behaved like a normal comet, with a tail and outgassing fitting expectations. This suggests that Oumuamua was unusual even among interstellar visitors. The discovery of these objects has opened a new field of study. Interstellar objects pass through the solar system regularly, perhaps a few per year, but they are difficult to detect. Future surveys with more sensitive telescopes may find many more, allowing us to study the debris and building blocks of other star systems. Oumuamua remains a mystery, a brief visitor that challenged our assumptions and left more questions than answers. And now, let the mysteries settle gently around you. We have journeyed through dark matter and dark energy, the invisible forces that shape the cosmos. We have pondered the Fermi paradox and the Great Filter, wondering why the universe seems so silent. We have encountered the cosmological constant problem, the matter-antimatter asymmetry, and the black hole information paradox, puzzles that reveal the limits of our understanding. We have glimpsed cosmic inflation and the multiverse, ideas that stretch reality beyond what we can see. And we have followed Oumuamua, a visitor from the stars that defied easy explanation. These mysteries are not failures. They are the frontier, the edge of what we know, and the beginning of what we might discover. Science is not a collection of facts, but a process of questioning, testing, and refining our understanding. Every mystery solved reveals new questions, deeper puzzles, and the universe grows richer with each layer we uncover. You are part of this story, a brief pattern of atoms and energy, aware and wondering. The universe gave rise to stars, and stars gave rise to planets, and on at least one planet, perhaps many, matter organized itself into life, and life into consciousness. You are the universe looking at itself, asking questions, seeking answers. And for now, you can rest. The mysteries will still be here tomorrow, waiting patiently in the dark. The cosmos has existed for 13.8 billion years, and it will continue for trillions more. Your questions, your curiosity, are part of its unfolding. So let your thoughts drift into silence. Let the vastness hold you gently. Let the unknown become a comfort rather than a worry. The universe is vast, strange, and full of wonders we have only begun to imagine. And you, here in this moment, resting and listening, are part of it all. Thank you for joining me on this journey through the cosmos. Thank you for your curiosity, your patience, and your willingness to wonder. If these nights of cosmic exploration have brought you peace, I hope you'll return. There are always more mysteries to explore, more questions to ask, more quiet journeys through the stars. Sleep well, dear traveler. Dream softly beneath the infinite sky. And know that somewhere out there, in the space between galaxies, in the hearts of stars, in the quantum foam of empty space, the universe continues its ancient dance, vast and mysterious and beautiful. Good night.